이번 시간에는 멀티팩터 모델을 해보도록 하겠습니다. 지난 시간에는 뭘 했죠? 스토캐스틱 디스카운트 팩터가 원팩터 모델로 이렇게 표현될 수 있을 때 CAPM이 나온다라는 걸 배웠죠? 그러면 이번 시간에는 이제 스토캐스틱 디스카운트 팩터가 원팩터로 되지 않고 멀티플 팩터로 될 때는 어떻게 되겠는가? 이 경우에 우리 크게 두 가지 모델을 유도하게 돼요. 첫 번째는 ICAPM, Intertemporal Capital Asset Pricing 모델이고, 두 번째는 이제 좀 더 많은 경우에 쓰일 수 있는 APT라는 모델입니다. 자, 그러면 화면을 공유할게요. Oops. The CAPM is a one-factor model as we saw in the last class. In that case, stochastic discount factor is just a linear expression in terms of the market portfolio. But more generally, the stochastic discount factor is a function of many state variables, say zk. So we can assume there are k different state variables, in which case stochastic discount factor is a marginal utility or the marginal rate of substitution. But then the consumptions in the future are a function of many different state variables, z. We can linearize the marginal utility or the stochastic discount factor using the Taylor expansion. Then we will obtain the following multi-factor expression where ft plus 1 is a vector of state variables z. That is how we get multi-factor model. Now, suppose that m can therefore be expressed as a linear function of the factor. And for simplicity, we will assume that factors are mean 0 and the average of the stochastic discount factor is just 1. You can always normalize it like this by demeaning the factors and put the average term to A. So A is going to contain the average of the factors. And we can normalize M because M captures the average magnitude of M captures the risk-free rate. And when we express the pricing model in terms of the excess returns, the magnitude of the risk-free rate doesn't matter. Therefore, it doesn't also matter what expectation of stochastic discount factor is. Now we can start from the expression using the excess returns, and we decompose this component as we have done many times before. Now f is a vector, so we must have had, so originally this, but then m is simply a plus b prime f. And because a is a constant, it is going to disappear. And this constant term, another constant term, is going to come out of the covariance. And then this is what we get. And to obtain the beta pricing model, we use the same technique, same trick as before, divide by the variance of f and multiply by variance of f. Why does this have matrix notation? Because f is a multi-dimensional vector. So therefore, we need to use variance-covariance matrix instead of the scalar variance f. Now, the intertemporal capital asset pricing model, the ICAPM. In this model, we assume that the stochastic discount factor is a linear function of multi-factors. So FT, or the factors, affect investors' portfolio choices, or it matters for the marginal utility. It matters for investors' consumption. Then we can obtain the same multi-factor pricing model. price of risk is given like this. More generally, we can express using the multi-factor setting. Okay? So it has many factors. The first factor is the usual market factor. This is the market. And the other factors are the ones that affect the investor's consumption in addition to the market factor. So these are other factors that affect the investment opportunity sets. Okay. Now, which affects the investor's overall wealth in the future. So the main departure from the CAPM of the ICAPM is long investment horizons and time-varying investment opportunity sets. Remember, how did we derive the CAPM? We used the two-factor model, right? I'm sorry, two-period model. So when the investment horizon is short, what investors care is only the market portfolio. Investors are going to consume everything in the next period. So what you care is your investment return in the next period. That is the reason why in the CAPM, the market portfolio was the only source of risk or source of the factor. But in a longer horizon, things are different. Investors care not only the market portfolio returns, but also the overall value of your wealth in the next period. That is going to depend on other state variables that describe the investment opportunities in the next period. In other words, investor wealth should depend not only on the realization of the market returns, so not only on the realization of your investment portfolio for the next period, but it also matters in the next period what your investment situation is going to be. Even if in the next period market collapses, if the futures are rosy, in other words, there are a lot of good investment opportunities, okay, then it can be a good state of the world. In other words, investors with long horizon is unhappy when news comes that future returns will be lower because the long-term wealth will be lower. Thus, the ICAPM says that investors will prefer stocks that will do well on negative news about future investment opportunities or future wealth. Okay. And these kind of assets will carry higher prices and lower expected returns. Why? If in the future there's a news about the future investment opportunities, okay, which is bad, okay, and there are some stocks that they will do well on those bad news, that kind of stock is a good hedge. It's a good insurance. Therefore, you want to pay more for such assets. So that the investment return should depend on covariance with news of future returns as well as the current market return. The main intuition here is that the state variables that affect investors' future wealth should also be priced. Then we're moving on to the arbitrage pricing theory, APT. It is developed by Steve Ross. And the APT starts from a statistical characterization of the realized asset returns. So that there's a big difference between APT and ICAPM. ICAPM originates from the economic representation of the stochastic discount factor, whereas APT does not rely on such economics. The only thing that you need is, in an APT, is that asset returns are characterized by a linear factor model. In other words, stocks tend to move together. So there are common factors that drive stock returns. And the key intuition is that the idiosyncratic component that has nothing to do with the factors shouldn't carry any priced risk. So that the priced returns or expected returns should be related to the covariance with the common components or factors. Again, unlike ICAPM, we get pricing implications without any economic structure to the factors. As long as there's a strong statistical relationship between the asset returns and the factors, we are fine. So what do we mean by a very strong statistical relationship? That is what is called the factor structure. So factor structure is simply a decomposition of asset returns into some constant component and common co-movement driven by the factors and also the idiosyncratic component. And you can always demean the factors and then obtain the following representation. And we will assume that the errors are uncorrelated across assets. Okay? And then we can derive the covariance between any two assets as the covariance coming from the common factors and the idiosyncratic variance component. Only we have the diagonal components because these are the variance of idiosyncratic returns, whereas all the off-diagonal elements are zeros. So it is important that expected return is only a statistical characterization of average returns, not derived from a prediction of a model. That is the big difference from the ICAPM. So there's no economic theory in the factor structure. So you come up with some factors. You give a thought without using any economic theory. And you come up with some statistical relationship of the returns that describes the common movement through the factors. Again, factors don't have to be motivated using economic theory. As long as stock returns can be expressed as in some factor structure, you're fine. The key assumptions that should hold is that the error terms or the idiosyncratic components shouldn't be correlated across assets, and the factors should be priced. In other words, the expected return on the factors should be greater than the risk-free rate. Okay? Or put it differently, the factors, the covariance between, not the covariance. So if the factor and the stochastic discount factor is orthogonal, then this is no good. These kind of factors are not the legit factors in an APT. So in an APT, the factors should be correlated with the stochastic discount factor. And we can always estimate a factor structure by running regressions, or we can even do what is called a factor analysis to come up with the factor structures. And as long as these factors, either it has come from, say, factor analysis or any other analysis or regression analysis, as long as the factor is correlated with the true stochastic discount factor, you can use the APT. So if there's no idiosyncratic component, as a very simple case, okay, so there's no idiosyncratic component, now we can see how the pricing is derived. Basically, the pricing of the asset I is going to be related to the pricing of the factors, because we assume that the factors are priced. The factors are correlated with the stochastic discount factor. Therefore, the combination of these factors is going to determine the pricing of these assets. Now, you put on the pricing factor on both sides, then you get prices of return is simply 1. And you can also show that pricing of some constant is constant divided by the risk-free rate plus the pricing of the factors where the linear combination is taken. And then you rearrange the thing and then you get the expected return as a linear expression of the betas. Okay? Now lambda is the factor risk premium. Now can you see why this is called the arbitrage pricing? Because the pricing is done with respect to the factors. So this is a relative pricing, not an equilibrium or absolute pricing. Now, in most cases, the exact APT that we saw in the previous slide is impossible because there is idiosyncratic risk epsilon. But you can still use the APT as long as the idiosyncratic risk is small. Now you put on the pricing parameter as before. Now the difference is this term. As long as the last term here is not very large, you can get some approximate pricing. Okay? How do we do that? How do we make the variance of the epsilons to be zero? By forming well-diversified portfolios, you can get rid of the variance of the epsilons. Okay? So you start with an equally weighted portfolio, and as long as n is large, the variance of the idiosyncratic component is going to approach zero, okay? And then you get the same APT pricing. Okay? So let's compare the APT and the ICAPM. Both generate multi-factor pricing models, but the motivations of the two models are different. The APT requires only a factor structure. Idiosyncratic risk shouldn't be correlated and should be fairly small. In other words, R-square should be high in the time series regressions, and it is a relative pricing model. Pricing is done with respect to the factors. So you come up with the factor pricing, the prices of the factors, and based on the factor structure, you can back out the pricing for the individual assets. But then the ICAPM is different. ICAPM requires that state variables should be related to the investment opportunity set or the consumptions of the representative agents. The investment opportunity determines the total wealth, okay? And because we start from the equilibrium model, it is an absolute pricing model. It governs how factors should be priced. But in practice, the distinction between the two is not very large, because even though theoretical motivations are different and are quite different, in practice, how they use them is pretty much the same. So there's one good example of the multi-factor model. Multi-factor model came along because there's abundant evidence that one factor CAPM fails to explain expected returns on, say, book-to-market and size portfolios, and we call this phenomenon anomalies. Okay? Anomalies that cannot be explained with the CAPM. And you can actually look at Jensen's alpha of each security. So this Jensen's alpha is simply the deviation of the expected return from the CAPM. And it is known that small stocks earn higher returns than the CAPM. And also it is the case that high book-to-market stocks or the value stocks earn positive alphas as well. Okay. Then came the Fama-French three-factor model, where in addition to the market factor, there's also the small minus large, which is the size factor, and high minus low, which is the value factor.